Hello everyone. So yeah, maybe too long the title, but yeah, I'm gonna read it. Like DAO options for cross-blockchain resource allocation, or maybe easier to understand. Share sequencer marketplace analysis from mechanism design perspective. So first we should discuss a ton of things here. What is share sequencing? What is cross-domain IB? What is blockchain or DAO auctions? What is cross-blockchain allocation? But let's start first with a brief introduction of what is cross-domain MEV. I don't know if you ever heard about this term. Did you? Some of you? Like, raise your hands. Not that many people. MEV? Okay, so it's the same thing, but now you don't just have one block, but you have multiple blocks. And what you would like to do is like, how do I coordinate those in a way that I can extract value? Very natural example would be, okay, like let's think about the domain as something more general than blockchain. Like centralized exchange is a domain that has some notion of time, things happen, things are appended. So you think that centralized exchange is a domain, text arbitrage is cross-domain MEV. You have to do one thing in one leg, you buy in one leg, and you sell in the other one. Maybe you have like, you don't bridge at the same time, maybe you just have like, liquidity on both chains, but my point is you could do this on one chain, but you could do this in multiple chains. Right now, for example, Kurak is doing very interesting research on like how you can do this between Polygon and Ethereum. I don't know if like I could say that, I had to say it. But yeah, like this is happening. This is real. This is a paper from Alejo Badilla. These are very big names, all of these. And yeah, they introduced the term. One of the interesting things they introduced is like, okay, what is the cost of different blockchains to try to coordinate and create something like PBS or something like, okay, let's try to build the most optimal block in terms of MEV, of how much I can extract from all the users. So yeah, that's an introduction to the cross-domain MEV. So share sequencer comes to place in like, okay, how we can actually build that and why we want to build it. That would be like the first two questions. So first, interesting thing of why I would like to build something like share sequencer is like, I could have cross-domain atomicity. I can, okay, I execute this transaction in this chain if and only if I also execute this transaction in the other chain. Well, this gives very nice features like interoperability, but also gives very nice features as like cross-domain arbitrage with having zero risk of like buying a shit coin that I'm not able to sell in the other chain, and that would be a disaster, right? And that happening actually would be like a negative externality. So due to MEV existing, we will not be allocating optimally the block space, and so we will be expanding block space for no reason. So that would be also a motivation of trying to sell blocks altogether. Another point, not that interesting for me, but because I'm not operating a rollup, but then yes, if you're operating a rollup, it's an important point. It's like you potentially increase the rollup revenue. It's like there is more of it, MEV, even more like MEV does not grow linearly in terms of the chains. It actually grows like probably super additively. Like the more chains you have, actually, the more and more MEV you will have. And so potentially, if you could share that in some way, like you could potentially extract more revenue. Yeah, like, and the last point is it's a way of like decentralizing the sequencer. So because if you are able to sell the rights of sequencing, it's somehow a way of decentralizing it. So what applications this could have? I don't know if you ever heard about the word intent. Yeah. So intent is like, yeah, it's very sounding word, but it's just like a transaction where you don't specify exactly how it gets executed or routed. So I want this, I don't care how I get it, can someone fill it for me? The point is like solvers, let's say I want to swap, but at the same time I want to bridge. So let's say I have ETH in Ethereum and I want Solana in Solana, but I have to bridge it and also swap it. And I ask for a network of solvers to do so, but they have some risk, right? Like, let's say like they want to swap part of your trade in the first chain and part of the trade in the second chain, because this is the most efficient thing to do because the liquidity is fragmented. But when they are bidding for doing so, like they have some risk of being one of the transactions executed and the other one not. So they would like to beat in a way of atomicity. So intent-based mechanisms, yeah, it's very good for intent-based mechanisms because you reduce risk. The more you reduce risks for solvers, you increase user experience, sort of. Another cool thing could be like to do cross-domain flash loans. So I think flash loans are very cool, and I think cross-domain could be even better. I wonder what type of attacks will exist, but that's another question. And yeah, at the end, maybe potentially efficient cross-domain extraction, whatever efficiency exactly means. But yeah, so what is the model? This is just like introduction. What would be the model for a shared sequencer marketplace? So we have, it's a two-side marketplace, right? Where in one side we have the rollups that are the sellers of the right of sequencing the rollup. So we have optimists, we have arbitrary, we have different kinds of optimists or actions, whatever. In this example, we have just two. This is one side of the market. On the other side, we have buyers that right now are called builders or sequence builders. In PBS are called builders because we have a one-to-one market, so validators and builders. Here we could call them sequencers. So yeah, one side we have the sellers of the rollups, we have the buyers, just yeah, like Beaver Builder, whatever. And in this model, we assume that the first side have a reserve price, so have a value that okay, I'm not gonna sell the sequencing rights unless it's this amount because I know I'm gonna be able to extract this. If I sequence it by my own, I'm gonna be able to extract this, so I'm not gonna sell it unless you pay me this. The buyers have combinatorial evaluations, so it's like, okay, if I'm able to sequence these and these and these, I value this way. If I just have subset, so very natural and combinatorial auctions. And in general, I will assume the evaluations are super modular, but actually it could be sub-modular as well because, yeah, there are complements and substitutes in these markets. Yeah, I'm also going to assume that they are derived from some public known distribution that I'm not going to fix. So we have at least some information on the evaluations. So yeah, that was the model I have in mind. So two-side markets, one sellers have evaluations on the item, and buyers have evaluations over all the items. And a shared sequencer marketplace is okay. How can I aggregate that? Okay, some people is buying for some subset of values, and the other ones are just selling it. How do I allocate it? So shared sequencer marketplace is just first a living language that fundamentally is like, what can I express? Can I express any combination of valuations? Can I express just one item? What exactly can I express on this market? Second thing would be like allocation rule. What do I allocate and to whom? And finally, a payment rule. It's like, okay, whatever do I allocate, how much we have to pay for it. And the idea of this marketplace is like, I should have the ability to bid for combination of items, right? Otherwise, it's not a shared sequencer. It's just like, yeah, you're selling it independently. So yeah, that is more or less the idea of what is a shared sequencer marketplace. And what would be the mechanisms like the desiderata would be like something very like some properties that are very like common in economics. That is like, okay, you want buyer individual irrationality. That is, okay, buyers do not pay more than what they bid for. Seller rationalities, these sellers obtain what they are asking for. Weak budget balance, a very important property, is like we are not subsidizing this marketplace. This is currently not happening in PBS. Just like an important point, this actually is not happening. So relays are subsidized, and there's a part of that marketplace that is being subsidized. A very important like notion that it's very like blockchain definition, like seal proof and shield proofness. So seal proof is like buyers cannot don't have incentives to bid more than once by different like identities. And shield proofness is that the seller doesn't have incentives to bid in the auction in order to obtain more revenue. And finally, it's like a very natural property is like we don't throw blocks to the bid. So it's like we always allocate to someone. And what we would like to do is like, so at least theoretically what we would like to do is like if we know the marginal contribution of which ones of the rollups, we can pay that marginal contribution. It's what we were seeing in the last talk with the searchers, how much the searchers were contributing. We would like to pay this marginal contribution. The problem in this marketplace is you don't know the marginal contribution, because I can always shield it in my own auction and make it think to the people that my actual block is way, way more valuable than it actually is. That's one of the difficulties. Another difficulty is I have to convince these people to come to the shared marketplace. And so at least I have to promise in expectancy that the profits that they are going to make is at least what they are making by their own. These are the two fundamental difficulties on this marketplace. And some examples would be like, well, the first trivial example is forget about sharing, just run two independent auctions. A second one could be like, try to run a combinatorial auction and make proportional payments. And a third one would be like, use a Chaplin payment rule to like know exactly how much you. So these are formulas for sharing the revenue. With your like all these measures should have the objective of maximizing welfare, revenue, or some notion of fairness. So welfare would be allocate the items to the ones that value the most. Seller's revenue, I think it's pretty well defined. It's just like maximizing the overall profit for the sellers. And fairness, I don't know. These are mathematical notions that I don't know how much time do I have.
Like 10 minutes?
10 minutes. Okay, then it's not that bad. Well, these are the formulas that define some notions yeah, it's like what it's called the variation price of anarchy. It's like in the worst case, in equilibrium, what happens? So okay, now I take suppose I know exactly how much people value the blocks, and I try to allocate it optimally. That would be the best case scenario. But in general, you don't have that information. And in general, games, when you're considering them in equilibrium, this does not happen. So the question is like, how I want to try to maximize, like, make as small as possible this cost of like coordinating like selfish agents when they are bidding in an auction. And while this is like price of anarchy, price stability have some difference, but it doesn't matter right now. And this is the formal definition. So it's like you fix it, like you take all the possible distributions. You may allow agents to play the game. So distribution of valuations, so how much they value the blocks and all this stuff. Allow you to play the game and compare how good are the equilibrium compared to the best allocation. And there, like the literature, there's a ton of results about this. Like second price auction is efficient. You actually give the item to the one that values the most. First price auction is actually very close to efficient, but when you don't have symmetric valuations, it's not efficient. And this is the bound. It was proved last year. A very long paper. Then you have the proportional allocation rule. That is what we currently have in proof of stake and proof of work. That has this bound on the variation price of anarchy. So actually, it's quite efficient, and that's good or bad, depends on how you think about these terms. And the last bound is for combinatorial auctions. That if you have a C approximate allocation, like combinatorial auction, that means that suppose you know the valuations and you run the algorithm, how far this algorithm is for the actual optimal, and when this is an NP problem, and so it has very bad bounds. But suppose you don't care about like computation complexity, and I never do, but I should do because this is blockchain. But you're very close to efficient actually, like, and this is also very interesting result. So yeah, like, in a computer auction, you like when you just have one seller, you can actually allocate it pretty efficiently. When you just have one seller. So one seller selling all the items. So imagine a shared OP stack. All the rollups are from the same from the same agent, so he can more or less allocate it very efficiently. This is also the case with base rollups, because in base rollups we have that the sequencer is the L1 validator, and so he's the same seller, and so we could actually have very good and very things close to efficient without the NP problem. But yeah, this is not happening actually in when you have multiple sellers. And for explaining that, I will to go back to something that is completely different from auctions. That is the Brest paradox. I don't know if any of you have ever heard about it. It's a very classical result that sometimes when you have routes and people is like driving, if you add more routes, you could even, like in equilibrium, and worse off. So that's very counterintuitive, but that can happen. This could be rephrased in the following way. If you have ways of agents to express their preferences, if you add more ways of expressing preferences, that maybe can be worse in equilibrium. Also, this is counterintuitive because there is a mantra in blockchain that you want users to express more preferences. And for this case, this is not true. And actually, for shared sequencers, in general, also not true. And this is one of the first results on the work in progress paper we are doing, is that for some auctions, like the Shapley value and the proportional payment, that current design of proportional payment is what specific has, have actually worse welfare and revenue than just selling the items separately. In other words, you're building things that have worse outcome in equilibrium. but this is just in some circumstances, like not all circumstances. And the idea is like all rollups in equilibrium want to push how much they value their own block, and by doing so, they end up not selling the blocks or in general, what happens is they end up being allocated to themselves and not being able to sell it. There is a math proof on the paper that you can check. This is the first result. All of this is for just-in-time auctions or for models where the valuations are known by the buyers and sellers. But the first result was that, and the second one is actually in the same line, where it says fundamentally that you, like the price of anarchy, whatever, in the worst case, you are not that far from selling everything separately. So we have two results. The first one is there are equilibriums that actually were better selling it separately, and the second one is like in terms of revenue and welfare for those specific auction mechanisms. And this result is like for every mechanism, worst case, you are not that far from selling it separately. Yeah?
What does DSIC stand for?
Dominant strong incentive compatibility. Dominant strong incentive compatibility. So it's like, it's a notion of like, you don't want to play the game. You don't want to gamify it. Like, you don't win nothing from being to playing strategies like overbidding or underbidding. You bid what you actually think the value of that is. So yeah, that's more or less the implication, and I think it's quite fun. And the idea is because like with supermodel evaluations, the problem is dual to like funding public goods and funding public goods that are non-excludable. It's very inefficient. So how we can fix that? Well, it depends on the model. You cannot, but if you are in a model where you can have some prior information, maybe you win some edge on selling the items before agents like realize their own value. So you not just know your expectancy, and if they haven't realized their value, you can maybe match it. So you have the right of buying all these blocks like 2 days before now, and right now you don't have enough information, and then you resell it in a secondary market. And yeah, for some cases we have some optimistic results on that, but we have to still keep working. So yeah, what is the future work and the open problems? So yeah, one of the fundamental problems of all of these is like how the rollups can conserve their sequencing rules. So if it's not a carnival sequencing rule, you're screwed. For example, first come, first serve. So second one is like how we can make this for more general evaluations and stuff, but this one seems hard. The third one is like how we can develop an online learning that, okay, we don't know the distribution because we never know the distribution. It's like just it's like abstract nonsense. Like we don't know the distribution, we have to learn it in some way. So I think like how we can develop online learning stuff that are robust against like adversaries in order to like learn how much we have to share the revenue between rollups. And finally, I think this is probably the most important one, is like how we can avoid winner takes all type of equilibrium. Because in slot auctions, you could have like agents trying to bid for multiple blocks, and then like start extracting like multi-block MEV, start censoring a ton of transactions, and a ton of things could happen. So one mechanism can avoid this type of equilibrium. So yeah, conclusions. Share security is good for intents, but it's very hard for, it's very hard to sell like complementary goods. In general, when you have multiple sellers and have a ton of cost on revenue and welfare, and maybe small auctions have some future, but maybe not. Yeah. So this is the QR. I don't know how to pronounce it of the work in progress. It's a GitHub. So if you want to like just leave your comments and this math proof is bad, just yeah. Give a review. At some point, I hope it would be in the archive. And for the ones that want to read a hardcore math, then this is. I would recommend the first one. I think the first one is the most important and relevant one of the that I have used. Yeah, that's all.